Hi, this is Mr. Hodgen. We're going to go over 9.3, talk about some of these properties and how to use them. So let's first just preview what we're going to be doing. Alright, so if you have a simple logarithm like this, simple meaning just numbers, no variables, there are ways to break it up into smaller pieces, let's say with 3's and 4's. You can probably see already, well, how can I get the log of 12 base 5 if I'm only having log 3 and log 4 available? This isn't quite going to be true since you always have a calculator, but it's just an exercise to get used to these properties so that when we throw in variables, we're able to move things around as needed. Okay. So the end result of all this is really going to be how to solve equations. And why do you want to split things up? Well, you might recall when you solve equations, you need to get the variables on one side and numbers on the other. So if we have something like this in the future, 12x, we're not going to be able to solve this very easily unless we're able to break these up and make it into, well, variables on one side and numbers on the other, and then we can solve it just like we always have. And I mean like this. We have an equation like this. How do you solve it? Well, we got to get the numbers over here. So we got to answer with the variables on one side and numbers on the other. And that's what all this will be useful for in the future. But for now, we're just going to use it as an exercise on numbers and just manipulating things around. But really, we'll just normally after this, we just put this in the calculator to get the answer. Okay, so let's first talk about some of the properties you already know. So recall that 2 to the third times 2 to the fifth equals 2 to the, let's see, I have 3 2's here, 5 2's here, so altogether we have 8 2's. I get 8 just by adding these together. So we're really just counting how many 2's we have altogether. Okay. So multiplying is forever linked, multiplying with exponents is forever linked to adding those exponents together. Okay. And when we start looking in the reverse direction with logarithms, we'll notice this is also true. So if we ever have a log of two numbers being multiplied, like so, it's going to be the same as those individuals' logs being added. Of course, these are all base 2. That's just the number we chose here. We're not so concerned about the answer right now. It's the fact that we can take two bases that are separate, combine them together. Okay? So if they're together, we can break them apart. And again, in the future, one of these will be a variable, and it'll be very nice to have the variable and the number separated so I can solve an equation and figure out the missing value. Okay? So the same will also be true for something like this. 2 to the fifth divided by 2 to the third. We know that, well, this equals 2 to the second, right? 3 of them cancel out. How can we get that? Just by using arithmetic. It's going to be 2 to the 5 minus 3. So whereas multiplication we added them, the division we subtract. So once again, we'll have something similar. So if we have the log, right, of 5 over 3, okay, that's going to be the same as the log of 5 minus the log of 3. And so you can see where these rules are coming from. They're not just created because they, well, we like them, but it's really replacing the bases, right, with this log 2. Okay. But it's the same idea. We're dividing 5 and 3, dividing 5 and 3. 5 minus 3, 5 minus 3. So I hope this helps understand some of these rules we're going to use. Okay. One more rule we're going to use. It's a nice little shortcut that's valuable. And it's more from observation that you get the same answer when you do it two different ways. So I guess we can use it. So let's say we have a log of 4 to the third power, and it's in base 2. Okay. All right. What does that equal? Okay, 4 to the third power would be 4 times 4 times 4, which is 64, right? And this is asking 2 to what power equals 64, right? So that's asking 2 to what power equals 64. And we know that we can do a little trial and error, figure out algebraically, but we'll know that 2 to the 6th power, 2 times 2 times 2 times 2 times 2 times 2 is 64. All right. Let's look at the same problem one more time, but from a different way. Okay. Let's just pay attention to this part right here. What if we just solve this smaller piece? Okay. What would log of 4 equal in base 2? So 2 to what power is 4? 2 to what power is 4? That's 2 times 2 is 4, so 2 to the second power is 4. So that's just simple 2. Now, we know our answer to this, since it's the same as this one, has to be 6. Well, what do you notice? If we just solve this one part right here, we get an answer of 2. But what's left over? A 3. So we can just take our answer that we got just by looking at this one piece only and multiply it by any exponent that might be there, and we get the same answer. Okay, so you're almost kind of ignoring the exponent up here at first, solving the simpler, smaller number problem, right? So finding out what 2 to what equals 4 is a little bit easier than finding out 2 to what equals 64. You know, you might have thought, well, I had to figure out how many times I had to multiply 2 to get 64. Okay, it's 2 times 2, maybe 5, maybe it's 6. You know, took a little bit more thinking, but with this shorter method, I only had to figure out 2 to what power equals 4, and then to multiply it by the remaining exponent, 3. So it's a little bit faster to get the same answer. Okay, that's why we like to use it. So those are the 3 properties you're going to be using today. And it's really just to manipulate things around so they're just easier to solve. That's the main point. And we'll introduce variables and solving equations later on. Okay. So let's go back. Once again, I'm multiplying 2 together. It's the same as adding those because they're exponents, right? When you multiply, you add exponents. And when you divide, you subtract exponents. Okay? And of course, these are all the same base. I could put log B, base B, base B. Okay. And lastly, I could try to simplify what this is and find out, well, you know, B to what power equals this number, but it turns out it's the same thing if I just figure out this part, right? Find out what that is first, and then just multiply it by P, so times P. So here we go. Let's try to use those. So for instance, right here, we want to break this up by multiplying or by factoring it down first. So I know 12 is the same as 3 times 4, right? 3 times 4. So if you're multiplying, though, that's the same as adding those exponents. So I have log of 3 plus the log of 4. And of course, we're using the same base right now. And if I know the log of 3 is 0.6826 and the log of 4 is 0.8614, I can go ahead and add those together and get my answer. So I can pull this up on the calculator here. Alright, so I have, let's fit this right here. I'm going to have 0.6826 plus 0.864. I know it's 1.544. And at this point, since these are approximate values, I'm going to have to actually switch from the equals to approximate. 1.544. Okay. And there we go. Now this is actually a lot of work just to get this number. We will introduce another formula that when you're using only numbers, you'll probably end up using this formula, and I'll give it to you right now just because it's for checking purposes. So there's also a change of base formula, which means, well, we can calculate this just on the calculator without doing any of this fancy, decomposing, 12 into 3 and 4 and looking up decimals and so on. So the fastest way you'll do this would actually be in your calculator, punch in log of 12 divided by the log of 5. And that will actually give you the same answer. You can verify that here. So we got the log of 12 equals divided by the log of 5. And yeah, 1.5439, but the 39 will round up to 4. So yeah, you do get approximately the same thing. Okay. So do check your answers using right here, using this as your check. Okay, another one. Let's practice another one. We didn't do any dividing. We didn't use the that shortcut rule, that third one we looked at. So let's practice with that. Okay, so here we go. So again, we're pretending we only have access to 3 and 4, log of 3 and 4. So we're kind of playing around saying, how can I get 3's and 4's from 100? Right? So, well, I know 4 times 25 is 100, so I can get a 4 that way. Let's do, yeah, like 25 times 4. And I know multiplication. Okay, so we're doing the same rule as we did before. Log of 25 plus the log of 4. Okay, so I know I have 4, so I know that decimal. This is going to be 0.8614. What about this? This isn't a 4 and it's not a 3, but what it is, it's 5 squared. So always when you see perfect squares or perfect cubes, if you see, what is that, 9, 16, 25, 36, or even cubes, 8, 27, 64, and so on, it's kind of like a red flag that it wants to be an exponent. Alright. So remember, we could find out, well, 5 to what power? 5 to what power equals this? It's the same as 2 times log of 5. So I can figure out what the log of 5 is first, right? And then just multiply that by the exponent 2. And by the way, these are all base 5. Okay, since we're not doing anything fancy, these are all base 5. We're assuming nothing is changing here. And then we can find out our answer. We can do 2 times whatever the decimal is for log of 5 and 2 times the, and the log of 4 and add those together. There's our notes from earlier. Okay, so 0.75, you might think, decimals. Okay, well, if we're keen on our fractions, you might look at 0.75 and say, oh, that's the same as 3/4, and there's your 3 and there's your 4. Just remember, if you're dividing, that means it's subtraction. So log of 3 minus log of 4. Of course, both base 5. Nothing's changing on our bases. And we can subtract those two numbers and get our answer. And again, it will be approximate. And you can check your answer using that formula I gave you earlier. That'd be log of 3/4 or log of 0.75 divided by log of 5. Okay. These two should be about the same decimal. Alright, and that's all you really need. Okay. You can see again, where are we going with all this? Why are we spending time breaking this up and using these approximate decimals just to get this answer? Well, what if we have something that's unknown? Then how can we find out what the missing value is? That's where we're going, and that's why we truly need all these properties.